Recently, we learned how to perform different operations on functions like adding, subtracting, multiplying them together, etc. And in light of that, it can often be helpful to be able to cancel out or undo something that you did with a function. The idea of undoing a function is covered by the concept of an inverse. So I have written down here that the inverse of a function is something that cancels it out, and the way it does it is by reversing the input and output. So it reverses what you put in and what you get out. So on this slide here, I have two different examples, and let's take a look at the one on the left. I give you a random function right here, and recall from like chapter 2, I think it was, this is a function because none of the x's repeat and have two different y's. So there's no input that has two outputs. We use the number 3 first, or sorry, we use number 3 twice here, but that's an output. That doesn't matter to us. All of our inputs are unique. They only have one output. And if you look at the graph, I went ahead and plotted those points. All of those points right there, this graph passes the vertical line test because it never chops more than once. So that is a function. To find the inverse function, and the symbol for an inverse function, the original I wrote down f of x up here. It's like f of x, but there's a little -1. It almost looks like an exponent right here, but you would pronounce this f inverse of x. So this little -1 that looks like an exponent essentially is the symbol for inverse. And all I'm going to do here is make a new table reversing my inputs and outputs. So it was -1, 2. Now I'm going to have 2, -1. 0, 1 is going to be 1, 0. 1, 3 becomes 3, 1. And 2, 3 becomes 3, 2. So I took my points right there and I flip-flopped my input and output values to get the inverse. So it's like the opposite of my original. Now my inverse is not a function in this example because my input of 3 has two different y values here. So that would be bad. This is not a function, but that doesn't mean we can't graph it. So I'm going to go ahead and do so. We have 2, -1, 1, 0. We'd be 3, +1, and then 3, +2. So that would be our function actually graphed there. On my second problem here, they give us just an equation right away, which you guys should recognize. That's a parabola, specifically y equals x squared. But let's say we wanted to graph the inverse of that. So if this is my original, I want to graph f inverse of x now. Now I could write down these points in a table and do the same thing, but I'm going to try to do it just by looking at my points here. This point is 0, 0. So if I switch my x and y coordinate, it's still going to be 0, 0. So nothing changes there. This point right here is 1, 1. If you switch 1, 1, it stays 1, 1. Things get a little more interesting though with the other points. The next one is 2, 4. 2, 4 is going to turn into 4, 2 when you switch it. 3, 4, 2. I have -1, 1. That's going to turn into 1, -1. And finally, I have -2, 4. That becomes 4, -2. So when I draw my graph right here, you get something like this. It actually looks like a sideways parabola there. And again, this will not be a function because it fails the vertical line test. You can chop through the graph twice at any of these spots right here. With both of these graphs here, there is a pattern. And there's a pattern with inverses in general, with how they look. If you were to draw in the line y equals x, that's a diagonal line like what you see me drawing in orange right here. On either of these examples, y equals x. If I actually turn my paper here, it's a little easier to see if I turn the board here. These graphs are the same on both sides of this line right here, y equals x. They are symmetric. Same thing on this example. It's the identical thing on both sides of my line. That's worth writing down as a note. If you graph a function and its inverse, so a function and its inverse, are symmetric about the line y equals x. So if you drew in that y equals x, that orange line that you saw in each example, you see that these are the same on either side of the line.